Hello everyone, welcome back. My name is Naresh Chetri. So today in this video, talk about algorithm implementation for the ECC algorithm we have talked in last video. If you hadn't watched that, please watch the part 1 what we have been talking in the previous video. So this is simply the part 2, the ECDHP, so the elliptic curve Diffie-Hellman Protocol implementation in Python programming language. Prerequisite, as I said before, to know about the ECDHP protocol, cryptography techniques, and Python programming basics. The algorithm for ECDHP, as I said, is Diffie-Hellman Protocol. So although there are several implementation and several use cases and several application of the elliptic curve cryptography algorithm, DHP, the Diffie-Hellman Protocol, the secret key between them sends by computing the shared key. The shared key match, and we say the message exchange was success. To import 3 libraries, one is the function module, but these two are the library to import, and the first one is the registry. So registry module, it is used to obtain keys and values from the registry height. Tynec, so tiny library that is used to perform arithmetic operation on elliptic curve, import the registry and the secrets. So the secret module is used to generate the cryptographically strong random numbers. This is the second one. And the third one is our compress ECC, which is a separate function module to calculate the elliptic curve's compress point. We define a function compress ECC and we compute the value as x1 and y1 using the hex function. It's used to convert an integer into the hexadecimal. We compute the public key, the x and y, using the hex function, and we return the value by adding those x1 and y1 values, retrieving all the slice from index to the registry is for curve, secrets for ka and kb, ECC function module to compute the ECC compress point. The ECC includes several areas like the Diffie-Hellman protocol, the digital signature, DSA, digital signature algorithm, online app, several, and also SIN. So technically the Bitcoin and the Ethereum is based on the ECDHP or the first thing is that we need to generate a public private key for message recipients based on the brain curve for the ECDH calculation. So elliptic curve Diffie-Hellman calculation, whose curve equal to get curve function, and that get curve function has the brain pool. So as I said again, this compress ECC is the function module compress ECC .py, and everything we work is inside elliptic curve VSP.py. We derive a secret share key and an ephemeral cipher ka and kb, the secret key for Alice and secret key for Bob. Rand below function, so again the rand below function returns a random number or the random integer between the range of 0 to n, which is passed exactly over there, and then we derive the same secret key for the pair of decryption, which we do is the pair of encryption. The only thing is that we pass that secret key compress ECC function. Every time you run the program, you won't get exactly the same output. Why? We have discussed over here. And then the key pair from recipient secret key, the ephemeral cipher, Alice and Bob, shared key A and shared key B, KA, KB, and secret key A and secret, something like this. On for the user in for the Alice, we compute the shared key A, it's KA into secret key B, and whereas we compute shared key B, it's KB into secret key A. So that's what it is shown over here. Shared key A and shared key B, they are utilized for both, for the both end as encryption and decryption, the compress ECC function. So this compress ECC function comes from over here, which is used several times. We wrap up with these values 4 times, okay? So 4 times in the sense, 2 times for public key and 2 times for the private key. As I again said, due to the ciphertext randomness, so you won't get the same output like that. But the thing is that the decryption and the encryption keys remain same. That means you will get the shared key exactly same. The program is here. First thing is we try to import all those 3 modules as we have said. The first one is registry, and which is taken from the Tynec, and the another one is secret, and another one in compress. So the compress we import as CP so that we can use the CP function as I have showed in the PPT all the 4 times. So cp.compress ECC for secret key and shared key. So is the compress ECC module. So this is just the function module defined where we compute x1 using the hex function for the public key x and the hex function for the public key y. Only in the case of y, we stores the remainder as 2 is the divisor and public key y is the dividend. On the value as x1 plus y1, you can retrieve the value from the all slice index 2. Here, when we come there, we take the corp, as I said, from the brain pool, so which is already defined there. We use for the ECDH calculation, and then we generate the secret key. So we use the KA for using the rand below function. The rand below function returns the random integer in the range of 0 to n. As I have said, the only thing is that the secret modules provide access to secure the randomness of the source. From that secret module, we have used that rand below function, which you can see we use to compute for the secret key for A, that is secret key for Alice, which we have used this over here, which we multiply by carb, and then which we have used the secret key for B for the Bob. The SC, as we import secrets as SC here, we compute the shared key. So shared key A, as we have said, computed, so Ka into shared secret key B, which we computed earlier. So that is the shared key by Alice, and then the shared key by Bob is KB into shared secret key, and we just print that values using the cp.compress shared key A and shared key B. Okay, so the only thing, if I run this, I can easily get the output. So may not get the same output exactly because of the randomness, as I said, differ, but still you can compare the shared key, so that will remain the same. As you can compare this, the shared key by Alice and the shared key by Bob, which remains exactly the same value. Equal shared key with both users Alice and Bob, that returns the value true, and if the shared key are equal, the message access success. This help, and I have downloaded the files and try to use it, but the only thing is that you need to install the tinynet. It's a tiny library, and import as I have said accordingly. I hope that helps, and once again, thank you for watching.